Greetings. Welcome to the seventh lesson in a series of short lessons on basics of power systems engineering. This lesson discusses conditions under which a voltage source or a current source transfer maximum power to the load to which they are connected. Consider a voltage source V sub S with an internal resistance R sub S in series with it and a variable load R connected to it. The current through the resistor is calculated as Vs over sum of Rs and R, shown here. The power delivered to R is found as I squared R. Substituting for I from top line, P sub R, the power consumed in the resistor R, is going to be equal to this expression here, V sub S over R plus Rs, quantity squared times R. The question is, taking V sub S and R sub S, which are the elements of the voltage source, to be constant, for what value of R the power transferred to it is maximized. I won't get into calculating it here, but a single differentiation of this equation with respect to R and then setting that derivative equal to 0 will show you that the power is maximized when R equals R sub S. In other words, when the load matches the internal resistance of the voltage source. Let's see a numerical example using the fact discussed here. Here we have a voltage source of 120 volts with an internal resistance of 5 ohms that is connected to a variable load. We are asked to set R, the load, to its power maximizing value and to calculate the maximum power delivered to it. We know from previous discussion that maximum power is delivered to any load connected to this voltage source when that load matches the internal resistance. So for maximizing the power to resistor R, we need to set R to 5 ohms. To find the power consumed in R, I'll first find the current through this circuit. The current is voltage over the sum of the two resistors, 120 over 10, which is 12 amps. And then the power in this resistor is calculated at I squared times its resistance R. So I have 12 squared times 5, giving me 720 watts as the maximum power that can be transferred to any load by this voltage source. As an exercise, you can change the value of the load from 5 to 4 ohms and calculate the power that's transferred to it. And again, you can change the value of R to 6 ohms and calculate the power transferred to it. I'll give you the answers on the next slide. You can pause this video if you want, and you can try finding them yourself before seeing my results. The answer for the 4 ohm load comes to 711 watts, and the answer for 6 ohm load comes to 714 watts. So the point is made that if you deviate from the maximizing resistance 5 ohms in either direction, the power transferred to it will go down from the 720 watts. You may have heard of impedance matching when connecting a speaker to an amplifier or connecting an antenna to a receiver. The reason for matching the impedance of the speaker to the output impedance of the amplifier, for example, is to have the speaker receive the maximum power possible from the amplifier. It should be noted that matching the internal resistance of the source is not the most efficient way of transferring power. Only half of the power delivered by the source is transferred to the load when load matches the internal resistance, and the other half of the power is dissipated in the internal resistance of the source. In other words, the efficiency at maximum power delivery is only 50%. It is easy to show that efficiency equals R over sum of R and RS. You see that equation here. For the circuit of this example, if R is increased to 15 ohms, efficiency is raised to 15 over 20 or 75%. You can see that here. Efficiency, if R were to be 15 ohms, is 15 over 20, which ends up at 0.75 times 100. That is 75%, so it's up from the 50% at the maximum power transfer. However, the power transfer to this load is only 540 watts compared to the maximum possible power transfer at 720 watts, which was found earlier, shown here. As the load resistance increases, efficiency approaches 100%, but of course the power transfer will go down at the same time. I'll take a short detour here for an introduction. My name is Fuad Albandi. I'm a PE in electrical engineering, licensed in the state of Maryland. This is the 7th lesson in a series of lessons on basics of electrical power engineering that I have published on the YouTube. You'll find my name and email address on this slide. You can visit my website at the link on this page for comprehensive modules on important topics in power systems engineering. My website link is own-your-destiny.mylearnworlds.com. I will now continue the lesson with example 2. Here we are asked to find the value of the load R that maximizes the power delivered to it from the circuit. One way of solving this problem is to remove R from the circuit, find the equivalent Thevenin circuit of the remaining circuit, and set R equal to the Thevenin equivalent resistance. Thevenin theorem is the subject of lesson 5, which you can review if you need to. In fact, there is an example in that lesson, lesson 5, in which the Thevenin equivalent of this circuit from the point of view of the terminal AB is found, and I will make use of it here. The Thevenin equivalent circuit looking from port AB is shown on the left. In fact, if we only needed the maximizing value of R, we could have stopped at finding the Thevenin equivalent resistance, RTH, equal 26.67, and we would have set R equal to it. However, since for this example we also need to find the power delivered to R, we need to use the whole Thevenin equivalent circuit, including the equivalent voltage source, to be able to do that. Placing R between points A and B of the Thevenin circuit on the left, let's set R equal to 26.67 ohms for maximum power. Next slide has the calculation of the power delivered to this resistor. First we find the current by dividing this voltage over the sum of these two resistances, and it comes to 1.563 amps. Then to find the current, to find the power in this resistor, we multiply the resistance time square of the current, and the maximized current comes, the maximized power comes to 65.1 watts. We will now turn our attention to the case of maximum power transfer to a load from a current source, shown here. This figure shows an unloaded current source along with its internal shunt resistance. To keep the lesson short, I will not get into as much detail, but will state the condition for maximum power transfer and do an example. The condition, not surprisingly, is quite similar to the case of voltage source. In other words, the power transfer to load is maximized when load resistance matches the internal shunt resistance of the current source. I'll work out an example. We'll repeat example 2, but we'll use the Norton equivalent circuit to find the answers. Norton theorem is covered in lesson 6. Next slide shows the Norton equivalent of the circuit after removing the resistor R. The Norton source current comes to 3.125, and Norton equivalent shunt resistance comes to 26.67 ohms. The power transfer to the load is maximized if the load resistance is chosen to match the Norton's equivalent shunt resistance. And that's shown on this slide. To find the power of the load, I'll find the current through it first. You can see that 3.125 is coming here, and it gets divided between two equal branches, so it's going to flow at half of the total current in each branch. We're interested in the current in this branch in order to find the power. So maximum power then is found as I squared times R, which gives us 65.1 watts. Comparing the results here with those of example 2, you'll notice that both the maximizing resistance and the maximum power come to the same answers as example 2, regardless of the use of Thevenin equivalent or Norton equivalent circuits. We have come to the end of lesson 7. This is Fuad Albandi, founder and instructor at the educational group Own Your Destiny. If you enjoy watching my channel, please click on the subscribe button. You can also visit my website at the link shown on this screen. Thanks for watching the presentation, and I hope to see you in another one of my presentations.